first, although everybody knows our next speaker, and the last one for this school year, Mark McLean from Stony Brook University. He'll talk about symplectic orbifold Gromov-Witten invariants.
Great. So yes, so I'll be talking about symplectic orbifold Gromov-Witten invariants, and this is joint work with Alex Ritter. It's very much work in progress, so I'm sure things will change once we write this up a little bit, but at least I'll convey the sort of basic idea of our work. So yes, so our aim is to construct Gromov-Witten invariants for symplectic orbifolds. So the usual counts were done already many years ago by Chen and Ruan, but you know, we could also try and define other counts. We wanted to do it our own way as well. So we wanted to define other counts. We also wanted to present these moduli spaces as in terms of global Kuranishi charts. Again, I'm sure, yeah, so this is what we wanted to do. So we wanted to put it in this sort of framework, and I'll explain what these things mean later on. This is also part of a much larger project with Alex Ritter. We were trying to, our aim was to sort of prove a kind of version, a sort of very weak version of the Crepant resolution conjecture. But the problem is that requires setting up a bunch of tools, and you know, first, and we wanted to sort of do it in this particular way. So that's part of a very big project which will take a while to complete, and this is sort of the first step. I should also say there's also ongoing work by Chekhu Mak and Son Sefardini and Ivan Smith. They're doing something with global quotient orbifolds. So this is the sort of this is the sort of motivation. Okay, so let me just remind you of some things. I'm going to be kind of sketchy. So, you know, an orbifold is just like a manifold, and it's just locally modeled on Rn mod a finite linear group action. So those are the coordinate charts, essentially. So for us, yeah, so locally you have some coordinate chart, it's some open subset of Rn. And on this open subset of Rn with some coordinates, you have some linear group action and sort of a map from the coordinate chart mod gamma to the sort of orbifold. Now the definition is much more complicated than, you know, the definition of a manifold, and I don't want to go into the details of that. But what we'll do is for us, we'll just think of orbifolds in terms of global quotients by Lie groups. So if you have a compact Lie group and it acts on a smooth manifold M with finite stabilizers, then you can think of the quotient as an orbifold, and for the purposes of this talk, that's good enough for us. So we'll just think of an orbifold as a sort of manifold modulo a Lie group, as long, and where the Lie group acts with finite stabilizers, and then you know, that you have sort of little slices to this group action. So for each point in our manifold, you have some submanifold which is equivariant under the stabilizer group of the point X, and you have a G equivariant neighborhood of X, so that you have the following isomorphism. So Sx. So you have this following diffeomorphism, And so you should think of the quotient of this manifold SSX mod GX, that's sort of locally, it's sort of like a locally modeling what M mod G looks like at the point X, essentially. So this slice theorem enables you to construct sort of orbifold charts of this orbifold, and so we'll think about orbifolds this way. Okay, so after shrinking the slice, you can assume that this slice has a global coordinate system with the stabilizer group acting linearly, and this is our orbifold chart centered at X. And so we'll think of it like this. And well, you know, that I really think of the orbifold as so sometimes I will distinguish between the orbifold itself and its underlying coarse moduli space, which is the set theoretic quotient. So, you know, this orbifold really has all this extra structure, these charts and so on. But if you're just looking at the sort of set theoretic quotient, then we have this underlying, I'll just call it coarse moduli space. And well, I didn't tell you what the definition of an orbifold is, but every smooth orbifold is a sort of global quotient like this. So we could always think of it like M mod G, and so this is what we'll do. Okay, so that's enough. That's enough about. Oh yeah. So now we have morphisms between orbifolds. So if you have two say global quotient orbifolds, M1 mod G1 and M2 mod G2, where G1 and G2 are Lie groups, then you have a morphism between them, and we'll think of it like this. So it's a diagram like this. So P is some manifold with a G1 cross G2 action, and you have a G1 equivariant map down to M1 and a G2 equivariant map to M2. So P is a smooth manifold, admits a G1 cross G2 action, and pi is a principal G2 bundle. So it's a principal G2 bundle that's G1 equivariant over M1, and you map it to M2, and this is what I'll think of as a morphism. And I suppose really it's an equivalence class of such diagrams. Maybe that's good enough for us for the moment. And so locally at the level of charts, if I have some sort of chart for one of my orbifolds, and I have another chart for my other orbifold, then this morphism induces a map between the underlying groups of these charts, and I get a sort of gamma 1 equivariant map from one chart to the other. So locally it looks like this, and this is what sort of a morphism looks like. So you know, you could think of you know, one way of thinking about these sorts of presentations of orbifolds is you have an orbifold, and M2 is like a principal G2 bundle over this orbifold, and you're pulling it back to M1, and this is what this P is, and so this is what these morphisms sort of look like. So this is the sort of objects we'll be interested in, and so well we're looking at symplectic orbifolds. So smooth orbifold together with a closed non-degenerate 2 form. And so you could think of this 2 form as a 2, you know, if X is like a quotient M mod G, where G is a Lie group acting semi-freely, then omega is some sort of closed 2 form on M, so that when you say restrict it to each slice chart, it's non-degenerate. And you know, we can define compatible almost complex structures and so on these symplectic orbifolds. And you know, they're contractible, so the usual things like this hold. So let us fix, you know, a symplectic orbifold with some compatible almost complex structure, and we'll fix some H2 class beta, and we want to look at moduli spaces of curves mapping to this orbifold. So to do that, well, we need to know what a curve is, and this is where you have to. This is where work of Abramovich and Vistoli comes in very handy. So Abramovich and Vistoli defined orbifold Gromov-Witten theory in the algebraic setting, and they sort of tell you what should be a holomorphic curve in this setting. So we define a complex orbifold just in, say, as a smooth orbifold with an integrable almost complex structure, and then the sort of domains of our holomorphic curves that we're interested in will be called twisted nodal curves. So this is how I'm going to define it. So a twisted nodal curve, it's a space of the form sigma tilde modulo an equivalence relation. So sigma tilde, sorry, this is sigma tilde. This is a one-dimensional complex orbifold. A one-dimensional complex orbifold. And this equivalence relation identifies pairs of distinct points. And in such a way that, it doesn't identify 3 points at once or something. It only identifies distinct pairs. And this is fine, but when you identify these points, you can't identify any 2 points. There has to be a balancing condition. So it says the following balancing condition holds. And so we need a balancing condition, so if we identify P with Q, then around P there must be an orbifold chart with some holomorphic coordinate Z. And well, because we're in complex one dimensions, there's the only group action you have is the cyclic group action. If you have a finite group, so you only have the sort of group action acting by roots of unity. And so around P, the group action, you have a Z mod KZ group action where you act by kth roots of unity like this. And then Q also has the same stabilizer group, Z mod KZ, and it acts by roots of unity, but with the opposite sign like this. Okay, so that these are the only points you're allowed. This is the balancing condition we need. Okay. And I'll explain a little bit why you need this balancing condition. So so sigma tilde I'll call the normalization of sigma. So it's just, it's how you usually normalize nodal curves. You just separate out all the nodes. And yes, and then the points we're identifying, this P is identified with Q's. Those points are the nodal points of our twisted nodal curve. Okay, so this is what the domain of our holomorphic when we define Gromov-Witten theory, we're counting J holomorphic maps, and so you need a moduli space of domains, and this is what the domain looks like. Okay. So this is what you replace. So when you do ordinary Gromov-Witten theory, this is what instead of just a normal nodal curve, you have this twisted nodal curve, and I would say and it's defined as analogously, but you just have to be careful what happens at the nodes. Basically, you have to have this balancing condition. Okay. So maybe I just want to motivate this balancing condition. So near a node, you could think of a twisted nodal curve as a well. It sort of looks like x times y equals 0 modulo a group action. And the group action, so x and y are holomorphic coordinates on C2. And so on C2, you have this group action, and the group action is the root of unity, say, acts on x and its inverse acts on y. So acts in the opposite directions on the x and y coordinates. Okay, so this is how you can think of what a twisted nodal curve looks like near a node. So I should say, so this is what it looks like near a node. It looks like this: x times y equals 0 modulo this group action, and this group action has this balanced condition here: g and g inverse act on x and y respectively. And the reason why this is good is because if you multiply x by g and you multiply y by g inverse, then it doesn't affect x times y. And what that means is it allows you to smooth the curve. So now you have x times y equals t, and that also, that curve is allowed, and it's a smoothing of this balanced node. So that's what this balancing condition does. It allows you to sort of smooth the node, and it's, and you can't really do it in a sort of nice way if you don't have this balancing condition. Okay. Great. Okay, and then we can define marked twisted nodal curves as well. So we just add marked points. For the purposes of this talk, I'm going to not worry about marked points. I'm not going to do anything much with them. But when you define Gromov-Witten invariants, you have to map your, you pull back cohomology classes via marked point evaluation maps, and you integrate and so on. But I'm not really going to worry about this too much today. So I'm just interested in building the moduli space and building a fundamental class on it. Okay, so I'll call sigma a twisted nodal curve with h marked points. And so what is a twisted nodal curve mapping to x? So x, remember, is our symplectic orbifold. So I had a symplectic orbifold, and I also had a choice of almost complex structure on it that was compatible with the symplectic form. So I will think of a twisted nodal curve as a morphism from the normalization of my twisted nodal curve to x, so that the following condition holds: the induced map on stabilizer groups is injective. We have this injectivity condition, and it descends to a continuous map. So it continuously extends over the nodes, the map. So this is what a twisted nodal curve mapping to a symplectic orbifold is. Okay, so the only thing that's, I would say, to keep in mind, which this, so if you naively generalized what Gromov-Witten invariants are for smooth symplectic, for normal symplectic manifolds, then you might miss this condition, and you sort of need this condition for the moduli spaces to sort of behave well. So oh yeah, so the genus is just the usual genus, the sort of the sort of the usual genus. Okay. And again, you can define well, we in Gromov-Witten theory, you count stable maps, and stability is defined in the usual way that you do for Gromov-Witten theory or Floer theory or whatever, which is you want finitely many automorphisms. That's for your moduli space to be well behaved. So an automorphism is a diagram like this. So phi is some isomorphism of twisted nodal curves, and it commutes with the map to x. Okay. Yeah, and if the domain has marked points, we fix these marked points. Again, this is usual in Gromov-Witten theory. And then so we let m gh beta of x be the space of these maps. So it's a space of stable J-homorphic maps, genus G, and it represents the class beta. Which H2, remember, beta is an H2 class that we fixed, an H2 class of the underlying coarse moduli space. So what we want to do is we have this thing. I've just defined it really as just a set. I mean, you could put it's not so bad to put a topology on this. You could think of it as a topological space. But what I would really like to sort of describe it in terms of global Kuranishi charts. And, you know, the other thing is that, you know, even describing it as a topological space, if I just described it as a set or something like this, it's, you know, there's information lost, such as the automorphisms of these curves. You know, you sort of really want to include this data. So I'm going to describe this as a global Kuranishi chart, and it will include it will sort of give all the data you need to sort of define fundamental classes in whatever appropriate theory you like. Okay. So you know, so an example is, you know, if M is a point and the group G is Z mod 2, so the orbifold is point mod Z mod 2, then you can look at the moduli space of twisted nodal curves with an appropriate sort of Z mod 2 principal bundle over it. And these sorts of spaces were described by Abramovich, Kortian, Vistoli, and this is all algebraic. So it's okay. So we wish to put a fundamental class on this moduli space, and so we can integrate pullbacks of cohomology classes to get Gromov-Witten invariants. And I use this word inertia stack, and I'm not going to tell you what that is. Again, you can look that up if you're interested in actually doing Gromov-Witten theory and so on. I'm just gonna focus on building a fundamental class for this talk. So the way I'm going to describe the moduli space is in terms of global Kuranishi charts. I could have defined a global Kuranishi chart to just be a section of an an Orbi vector bundle over an orbifold. I could have just defined it like that. But instead I'm going to define it in a sort of as a sort of global quotient like this. So I'm going to think of it as a tuple where I have a Lie group G, I have a manifold T, I have a G equivariant vector bundle E over T, and a G equivariant section. So G acts semi-freely on T, and E is a G vector bundle over T, and we have a G equivariant section S. So as I said, if I quotient T by G and I quotient E by G, and I have the induced section, you know, this is just a section of an orbifold. Essentially, that's what a global Kuranishi chart is. But I'm presenting it as a global quotient, you know, manifold mod Lie group acting semi-freely. So I'm going to call T the thickening and E is the obstruction bundle. And sort of morally, you know, S is morally something like it's morally representing something like the D-bar operator or some sort of very roughly. Okay. So we say that the global Kuranishi chart GTES models our moduli space if this moduli space is, say, homeomorphic to this. Actually, you could say more. You could think of MGH beta of X as some sort of Orbi like topological space. So you include the data of the automorphisms of the curves in M, and then you really want the stabilizer groups of S inverse of 0 mod, the points in here, the stabilizer groups, you want them to sort of match with this. And so it's a really homeomorphic, really it should be homeomorphic as sort of topological Orbi spaces. So that in that sense, that's how we're going to model this moduli space. Okay. And then once you have this structure, then you can build a fundamental class. And I'm not going to talk much about this. I'm just going to be very rough. So the fundamental class is given by, you take the fundamental class of T mod G. So T mod G is an orbifold, and so you put a fundamental class on it, and you cap it with the Tom class of the vector bundle. And so T mod G is the fundamental class, say, in G equivariant homology of T. So for instance, if you're working over Q, it's just homology of the quotient. But if you're working with something like K theory, then you work with G equivariant K theory, and you can put a fundamental class on that. We talk about this in my paper with Ivan Smith and Mohammed Abu Zaid. So you can build a fundamental class once you have this structure, and it's not so bad. And yeah, so you also need an appropriate orientation for sorry, this should be the tangent space of T minus G and E. And again, this is explained in say my work with Mohammed Abu Zaid and Ivan Smith in another paper just with normal Gromov-Witten theory. So what I want to explain for the rest of the talk is how do you construct this global Kuranishi chart? Yeah, so how do you do that? Okay. So what I'll do first is just explain what happens in a simpler setting, where X is just a smooth manifold. It's not an orbifold, it's just a smooth manifold, and I'm just looking at genus 0 curves. And then we'll just modify this construction to do the orbifold. We'll explain how to modify it to do higher to do orbifolds and also higher genus curves. So in this setting, this construction was due to myself and Mohammed Abu Zaid and Ivan Smith. Although what I'm going to say is slightly different, but it's morally the same, similar. Let's say similar. So what we want to do first is we want to look at this space FHD. So this is a moduli space of degree D curves with H mark points mapping to projective space, and whose image is not contained in a hyperplane. Okay, so this condition here, the image not being in a hyperplane, that's the same as saying that if I take a basis of sections, so I take the coordinate sections, for instance, the basis of sections of O1 on PD, and I restrict to the curve, then I get an induced basis for the pullback of H1 on that curve. So I get an induced basis for the pullback of O1 on that curve of holomorphic sections. So that's equivalent to that condition. You can also think of FHD as a kind of moduli space. So you could think of it as a moduli space of genus 0 curves together with a line bundle over that curve and a basis of sections of that line bundle, up to some sort of equivalence. And that's what this is. It's like a moduli space of curves with a line bundle of degree d and a basis of sections of that. So if I have a genus 0 curve with a basis of sections of some line bundle over it, degree d line bundle, then also the line bundle has to be h1 of that line bundle has to be 0. And if I have those conditions, then I get an element of this moduli space. So this is a smooth quasi-projective variety. And over it, I have a universal curve, which I'll call CHD. And I'll write C0HD for the complement of its nodes. Okay. Great. So I have this moduli space of curves, and what is the purpose of FHD? The purpose of it is I want, you know, in Gromov-Witten theory, what you're doing is you're looking at some moduli space of equivalence classes of maps from a domain to some symplectic manifold, and the problem is the domain is sort of arbitrary. You know, it's any genus 0 curve, and you know you can build those in all kinds of ways, and you know you really want some fixed finite dimensional family of curves in which to model these domains. And you know, if you want to do analysis or something like this, that's what you really want, and this F plays that role essentially. Okay. So so the next thing I need is I'm going to look at C0 cross X, and over that space I have a vector bundle, and the fiber over a point Px is a space of anti-holomorphic maps from the tangent space of the fiber of C at P to Tx. Okay. So this is some vector bundle. And then I'm going to construct something called a finite dimensional approximation scheme. So it's a sequence of equivariant maps. So PUD+1, that's the group of sort of isometries of PD. So that acts on F, that acts on C, that acts on this space. And I have these equivariant maps to they're linear maps. So sorry, they're equivariant linear maps from a vector space V mu to the space of functions, space of compactly supported sections of this vector bundle. And the domain of this map is a PUD+1 representation, and I want the union of their images to be dense. So, you know, one thing to make sure is, can you construct these maps? Sorry, yeah, I should put the word linear here. Just they're linear maps. You know, to construct these maps, you can do something like look at, say, so they exist because you can do things like construct say you have an equivariant, you choose an equivariant metric, and you look at eigen sections of some equivariant Laplacian of my vector bundle, something like this, and so you can do that. So this thing exists. So once I've chosen this finite dimensional approximation scheme, I can construct a moduli space, and I'm going to call it the pre-thickened moduli space. And in this case, it's basically the same as the thickened moduli space, but in higher genus, it's not. So I'm going to define a moduli space called the pre-thickened moduli space, and it's the following thing. It's the space of tuples U phi E phi is an element of my moduli space of curves mapping to CPD. And then U is a map from the corresponding curve at phi to X. And E is an element of this vector space V mu. So I choose some large mu. Mu is some very large number I've chosen. And so mu is fixed. It's just going to be some fixed, very large natural number. And it satisfies this equation. Okay. So what I've done here is I have essentially what I have is I have a family of domains that I've built. Okay, some moduli space of domains with some extra data, which is a vector, which is a line bundle with a basis of sections essentially. And I also have this family of domains, and then I have a moduli space. Then I have a family of equations, which is this family of equations. And this family of equations is parameterized by V mu. So I have a vector space and a family of equations parameterized by this vector space. And this family of domains, and I also have the space of all maps from from elements of this family of domains satisfying this family of equations. So essentially the point of this construction is you want to take the d-bar equation and sort of make the problem with the d-bar equation is that the linearization of that d-bar equation is not surjective, and you want to make it surjective. And the way to make it surjective is to enlarge your family of equations. So instead of having d-bar is 0, you now have d-bar is something else, and that something else varies. And if you vary it in a large enough family, you get sort of surjectivity, and you get a nicer moduli space. And this is what this pre-thickened moduli space is. And when you do when you do analysis, so you want to prove when you build this global Kuranishi chart, this is where all the analysis is going to be, at this level of this pre-thickened moduli space. So once you've built it, you do your sort of analysis. In this case, you read Macduff Salamon's book or whatever, and you build this and show that it's a manifold. And once you've done that, after that, you do there are some extra steps to make it a global Kuranishi chart. Use this to become a global Kuranishi chart. And this has some induced topology. So this is the Gromov topology, but you can actually, in this case, you can make it very explicit. It's the Hausdorff metric. It actually has a metric. You choose a metric on C and X. You take the graphs of all these maps and you just look at the induced Hausdorff metric on the graphs of these maps. And that's the same as the Gromov topology. Okay.
And C and F here are all for the fixed H and D that you picked.
Sorry, say that again.
The F and C here are for the fixed H and D that you chose.
Yes, yeah. So I'm fixing a lot of data. So I'm fixing J. I'm fixing the symplectic orbifold. I'm fixing the number of marked points. D. I should have said this. D at the moment is fixed, but it will be chosen later in terms of beta. So D. In a minute, you'll see that D is actually some number involving beta. It's going to be like beta paired with omega plus 1 or something like this. Okay.
Thank you.
Okay. So you could try and build from this pre-thickened moduli space. You could try and build your global Kuranishi chart. So you could try and guess that the obstruction bundle is V mu. So this obstruction bundle E, you could think of this pre-thickened moduli space as your thickening, and you could try and put an obstruction bundle over it, which is V mu. And then when the section is 0, there'll be a natural section of it given by E. And when you set E equals 0, you get J holomorphic curves. So if you look at this previous equation, you set E equals 0, then lambda mu of E is 0. And so then this d bar of U is 0. And so it will be holomorphic curves. And that, you know, this is a good guess of what could be the moduli space of curves, global Kuranishi chart. But the problem is it's sort of too big. It would probably be fine if our group G was PGL or something, but there's no way this will work, because this finite dimensional approximation scheme is you can only make PU equivariant maps. The group has to be compact. You can't make it non-compact. So if it was PGL instead of PU, you could probably make this work, but it doesn't quite work. So we need to do something else. So we need to sort of reduce the group from PGL to PU, and so we need some more structure basically. What we need to do is yeah. So I'll explain what we need to do. Okay. Yeah, I suppose a very rough analog of what we're doing here is, you know, if you had some sort of, I don't know, like, well, no, I won't say this. I think it won't be very helpful if I say that. So, okay, so what we need to do is we need some more data. So we need to make another choice. So the other choice is we choose a Hermitian line bundle L over X, whose curvature form tames J. Okay. And, you know, these such things exist. What you can do is, yeah, you can do things like, you know, omega is just some arbitrary symplectic form. It might be irrational, but you could perturb it very slightly so it's rational and it tames J, and then you can scale it so it becomes integral. And then once you have an integral symplectic form, then you can find this Hermitian line bundle. Okay. So now I'm going to fix D. So D is C1 of L paired with beta plus 1. And I'm going to define something called a framed curve. So a framed curve is a triple U sigma F. U is a smooth map from, well, I should say a nodal curve. I didn't say this. A smooth map from a nodal curve to X, representing my class beta. And F is a basis of sections of H0 of U star L. And yeah, I've chosen things so that this is sort of the largest possible basis. So H1 of U star L is 0, and this is the sort of the largest possible basis you can have. Okay. So if I have a basis of sections of a line bundle, then I get a map to PD, and it's the usual map. You know, if I have a basis sections of line bundles, I have a map to projective space, and so this F, which I'm going to call the framing, so F is called the framing, and this framing induces a map to PD. And so, yes, so essentially, given a framed curve, I have an element phi F of this curly F, this moduli space curly F. So this map here actually lands in curly F. So the image is not contained in a hyperplane. Okay. So in particular, the good thing about this framing is, this framing F is, I have an identification of the domain of my curve with an element with a fiber of my universal curve over this moduli space of maps to CPD. So you know, before I had an arbitrary domain, but now I've identified it actually sort of uniquely with this fiber once I have this framing.
So sorry, here L is a chosen line bundle on X.
Yes, L. Yeah, let me go back. So I fix a Hermitian line bundle whose curvature form tames J.
Yeah.
Okay.
Mm-hmm.
Yeah, there's a lot of notation, I'm afraid, and it's going to explode I'm sorry. So yeah, I'll try and remind you of previous things. Okay, so the next thing I'm going to do is look at the space of Hermitian matrices, and what this is going to do. See, remember, I wanted to quotient by PGL, but I couldn't quite do that because everything I had was just PU equivariance. So I need some vector space sort of telling me how far I am from being from PU. So what I do next is okay, so Fi and Fi, F0 to Fd, those are the elements of my framing. Okay, so let me go back before I carry on. So remember, a framed curve is just a map from a smooth map from a nodal curve to X, and it has this framing, and this framing is a basis of sections, little f0 to little fd. Okay, so if I have this basis of sections, then I can form a matrix. I pair these sections up using the Hermitian metric, and I integrate over a form like this, and I get a matrix. And what I want is this matrix to be so what I really want is this matrix to be orthogonal, but it's not always orthogonal. So this is what I want. So I have this matrix A sub F. Okay. So now I can define the thickening. So the thickening T is the space of isomorphism classes of tuples U sigma F E, where U sigma F is a framed curve. E is an element of V mu. V mu is this finite dimensional approximation scheme, so that this is in the pre-thickening. Okay, so the thickening is like, yes, so yes, so basically what I have is I mean, in this case, it's essentially the same as the pre-thickening. But the only difference now is I have this matrix A sub F. And this Hermitian line bundle enables me to tell me how far away these sections are from being orthogonal, essentially. Okay. So this is PD, sorry. So the group G acts on this thickening. Now the obstruction bundle before, the guess for the obstruction bundle was V mu, but now it's H plus cross V mu. And the section sends this tuple to this matrix, comma E. Or I should really put X inverse of this matrix, comma E. And then my claim is this is the global Kuranishi chart for genus 0 curves. Okay. So what I want to do is, So there's a theorem which says essentially this is a global Kuranishi chart. There are some details missing, like this thickening. You have to shrink this thickening so you only look at curves that are very close to being holomorphic. So you have to sort of do things like that, and then if this, and then there's loads of choices. You chose a Hermitian line bundle. You chose this finite dimensional approximation scheme, and then you chose a particular element of this finite dimensional approximation scheme. So you chose some integer mu, and then this Hermitian line bundle really should be of sufficiently high degree, because if the degree of it is too low, then you don't get any frame. You want all your holomorphic curves to have at least one framing. So your Hermitian line bundle has to be of sufficiently ample. So there are various extra details that I'm missing. from this presentation. But essentially, this is how you build the global Kuranishi chart, and it contains all the data you want. So for instance, it includes all the data of, say, the automorphism groups of the curves and everything like that, and they all match up. So it works out pretty well. And so once you have this, you can build, your K-theoretic virtual fundamental class or whatever you want from this structure.
May I ask?
Yes.
So basically, you had this V over the pre-thickening. You said, okay, that's too big because we have to mod by a compact group.
Yes.
So, and then what you did was you made them both bigger. So you added the framing to your T, and then you sort of increased the V by adding this H plus.
Yes.
And this is now okay.
Yes. Yeah.
Okay,
Yeah.
thank you.
I suppose this is a downside of some of this stuff. Yeah, we solving my problems by adding more stuff until it's sort of, yeah. I mean, what I'm trying to do, like, a sort of rough analogy is like, it's very rough. It's like, if I have some sort of algebraic variety or something, and I have some, say, GL acting on it, and I look at the quotient, I can construct like a GIT quotient or something like this. But the other way of doing it is you choose a moment map, and then you choose a sort of pre-image of some point in the moment map, and you quotient by a compact group. And it's sort of a little bit like this. I'm sort of doing something like this. But the problem with us is that we didn't even have GL acting on, GL doesn't really act on this space in the first place. So it doesn't quite work like that. But it looks a little bit similar, I suppose.
Thank you, that helps.
Okay. So what I want to do is explain how to do this for orbifolds. And I don't know how much time I'll have to explain all of this, because again, there's a lot of notation. But there are two problems. The first is twisted nodal curves don't map to PD. Remember, you want this map to be injective, this map of stabilizers to be injective. So, trivial stable, PD has no stabilizers. It's not an orbifold. So I'll address this problem, and then the second problem I'll talk about it, although I don't, if we have time, I'll explain how to deal with it, is line bundles. We sort of really use the fact that there was a unique line bundle of each degree on genus zero curves, and now, at least on P1 or something, but now if you have a higher genus curve, there's a sort of moduli space of line bundles, and this causes a problem. Yeah, I'm not sure if the way I'm going to solve this in this talk or in our paper is the most efficient, but it works. The Mohan Swaminathan and Amanda Hershey have a nice way of resolving this problem as well. And also my paper with Ivan Smith and Mohammed Abuzaid solves this problem, maybe in a slightly messier way, but okay. So let's deal with the first problem. So what I'm going to do, so the idea is to use the work of Ross and Thomas. So what Ross and Thomas do is, if you have an ample line bundle and you have a basis of sections and it satisfies appropriate properties, then you can, say, embed your variety into CPN. And what Ross and Thomas do is they do the same thing, but for orbifolds. Now, you can't do this naively. So the problem is that if I just took some sort of naive line bundle over some orbifold, and I just took a basis of sections of that, and I tried to sort of map things to I tried to use that as a map. Well, I wouldn't get a well-defined map. Problems will occur at the orbifold points, and the reason is because, you know, if I just had a naive line bundle over an orbifold, then the sections might sort of vanish at the orbifold points, and that causes problems. So the first thing to know is that instead of mapping, so what Ross Thomas say is, instead of mapping to projective space, you should map to weighted projective space for some appropriate sequence of natural numbers. Oops, W0 to WD. So we're going to map to weighted projective space, and weighted projective spaces can be orbifolds. So that's good. There is a downside of this, which is the orbifold points are cyclic singularities. So, you know, you're not going to map an orbifold with stabilizer groups that are not cyclic. However, if you have a twisted nodal curve, that's fine. Everything is cyclic. All the quotient singularities are Z mod KZ, so it's fine for us. Okay. So we're going to assume we have a compact orbifold with only cyclic quotient singularities. We're only interested in the one-dimensional case because we only want to map twisted nodal curves to this weighted projective space. So I want to tell you what it means for a line bundle to be ample in an orbifold. So a line bundle is locally ample if the stabilizer of each point acts faithfully on the fiber at each point. Okay. So remember, like locally, I mean, I didn't really define a line bundle, but locally over an orbifold chart, a line bundle, you know, an orbifold chart is given by a coordinate system with some group gamma acting linearly on it. And locally, a line bundle is like a gamma representation over that chart. So when the gamma acts, it also acts linearly on the fibers as well. And you want that action to be faithful. And then we call it globally positive if some power of this line bundle is ample. So is ample, say, on the coarse moduli space. So if you have a complex orbifold, the coarse moduli space is some variety, and you want L to be some power of L to be the pullback of a bundle from this coarse moduli space. And so it's a pull. So L to the n is sort of like a naive vector bundle where, you know, on orbifold charts it doesn't act. Gamma doesn't act on the fibers. Okay, so if you take some, you know, appropriate power of L, then the stabilizers will act trivially, and you can put it's a pullback from the coarse moduli space. Oh, I think the hour's getting close to up. So L is orbit ample if it is locally ample and globally positive. So now what we do is we do the following thing. So for each power of L, we let Ni be the rank of the basis of sections. And I'm going to do this. This is a little bit overkill, but I'm going to define a K-framing to be a tuple of sections of L to the I, where I runs from K to 2K. I think in Ross Thomas, they go from K to K plus N, where N is the sort of the least common multiple of all the stabilizers. So, but I'm going to just go from K to 2K, and K is some very, very large number. And then I have an appropriate weighted projective space. So it's massive. It goes from the weights go from K to 2K, and there are Ni copies of K plus I, like this. And so now with this framing, I have a map to weighted projective space, and I sort of define it in a very similar way to how I would do it to projective space. So the key point is, instead of looking at a basis of sections of a fixed line bundle, I look at a basis of sections of a range of powers of the line bundle, and the range starts from some high number and it finishes at some even higher number. And then I map to weighted projective space, and and you do it in the same way essentially. And so, you know, this is an embedding for K large. Okay, so I've almost run out of time, so I've been a bit slow. Okay, so maybe I'll just very quickly say some things. So now you want to build your global Kuranishi charts, and the basic idea is, instead of using framed curves, you just, instead of using framings in the old sense, you use framings in this new Ross-Thomas sense. So you have your symplectic orbifold. Now yeah, there's some extra stuff you need. So first of all, I want to choose a locally ample Orbi vector bundle, and I want to choose a Hermitian line bundle as before. But the line bundle is a sort of pullback of a line bundle. Let's see. Okay, so I'm almost I should just maybe I should just say something. Let's see if I can say something. Yeah, so let me see what I can say. Okay. What shall I say? Yeah, okay, maybe I'll just finish the talk with this. Okay, so I'm just going to highlight this here. Okay, this formula here. Okay, so ignore all the other stuff. What you do is you have a Hermitian line bundle L of your orbifold, but it's just a honest line bundle. So the stabilizer groups act trivially on the fibers. So it's a pull. So it's just an honest line bundle, and I pull it back to my curve. So I have a curve U. It's a twisted nodal curve mapping to my orbifold, and I pull back this Hermitian line bundle L, and then I tensor it with the log canonical bundle twisted by all the marked points. Okay. And this bundle I call L sub U, and I define a framed curve to be a smooth map from a twisted nodal curve to my orbifold, with a framing in the sense of Ross-Thomas, essentially. And this is this is the sort of idea, basically. And this at least deals with the problem that you have an orbifold. There's one other problem with an orbifold, which is I really want my global Kuranishi chart. I really want the thickening of my global Kuranishi chart to be a manifold, and even if I do that, I don't quite get what I want. So I also need to choose a framing of this vector bundle as well, a framing in sense of Ross-Thomas. And this what this does is it sort of fixes it ensures my curve doesn't have any automorphisms in the orbifold sense, because I could have a curve mapping to say a point with non-trivial stabilizer, and somehow that non-trivial stabilizer could give you automorphisms of the curve, and so I need to fix that as well. Yes. Okay, so my talk's an hour long and it's 20 past 10, so I'm going to stop here and go to questions.
Thank you very much. Questions? I mean, I can kick off by asking about the dependencies. So there's a choice of a bundle, a choice of framing, a choice maybe of an embedding into a projective space.
Yes.
is there anything known about the dependencies, the
Yes.
relation between different choices?
Yes. So everything is unique up to explicit equivalences. So if I have a global Kuranishi chart, there are various operations I can do on it. So one operation is I would call germ equivalence, which is I just shrink the thickening around the zero section, and that doesn't change anything. So that's germ equivalence, because I'm only interested in the zero, the germ of the zero section. So, and then
equivalence in like you have a category of.
Yeah, there's a
vectors,
category
or...
of these charts. Yeah, there's actually a category of global
Okay.
charts. And then there's other things like stabilization, which means I can add an extra vector bundle and take the total space of it over the thickening and take some, and then if I enlarge my thickening by a vector bundle, I have to enlarge the obstruction bundle too to get something of the same size and choose add a diagonal section. This is called stabilization. And then there's another thing called group enlargement, where I sort of enlarge the group. So you take some principal bundle, you pull it back to the principal bundle, and you have a larger group action. And up to those three operations, everything is unique. So all of those choices I made, line bundle, finite dimensional approximation scheme, all of that, if I choose different things, I will get an equivalent global Kuranishi chart up to a sequence of those operations and their inverses.
So genuinely an equivalent chart, not just, let's say, an equivalent notion of a fundamental class.
Equivalent chart, yes. You could think of, yeah, I mean, yes. You could even think of, you can look at, you could think of a sort of universal kind of fundamental class where you have global Kuranishi charts up to cobordism, where the cobordisms are also global Kuranishi charts, and you're that's sort of like you can use that, you can do Gromov-Witten theory valued in that sort of ring, and that's it's a sort of universal kind of ring, and you could work with that perfectly fine. It's impossible to do any calculations, but
Awesome. More questions?
May I ask you, so you mentioned as a potential application, if I understood correctly, discrepant resolution
Yes.
conjecture.
Yes.
Could you please elaborate?
Oh, yeah. So, yeah, this is a big project with me and Alex are doing. So maybe 5 years ago, I proved that birational Calabi-Yaos have the same small quantum products, and so if I have two birational Calabi-Yau manifolds, then conjecturally their Gromov-Witten invariants should be the same in some sense. You have to be careful what the word "the same" means. So up to some equivalence, they're the same. And I proved a special case of this using Fleur theory. So there's a sort of symplectic I use sort of essentially relative symplectic cohomology. So if you have a closed domain inside a symplectic manifold, you have this sort of symplectic cohomology group, so I use that as a tool to prove that birational Calabi-Yaos have the same small quantum cohomology, and so you could ask the same question for birational orbifolds, Calabi-Yau orbifolds, and that includes discrepant resolutions. And so, but to do that, I want to develop the sort of tools first. So I want holomorphic Gromov-Witten theory, and I wanted to do it sort of this way, and then I wanted to do Hamiltonian Fleur theory, and then we would try and build the equivalence, sort of in a similar way to how I did in my paper, but there are additional complications which make it harder, but sort of technical complications. But this is the sort of idea.
So what eventually you plan to develop Hamiltonian Floer theory on orbifolds?
Yes, yeah.
I see, thank you.
I have a question.
Yes.
So if you're in a situation where you have a symplectic manifold with a group action, you could consider maybe the quotient is an orbifold. You consider an orbifold Gromov-Witten theory, but you could also consider a G-equivariant Gromov-Witten theory. So really two questions. The first one, can the construction you outlined of virtual fundamental classes, all of this, can this be carried out to give equivariant Gromov-Witten invariants? And the same question is, how would they match up or be related to the orbifold Gromov-Witten?
Okay. Yeah, so let me, yes. So I won't show anything on my slides. So everything let's say we're doing genus 0. Let's say we have a symplectic manifold with a group action on it, like a Lie group acting on it in any way you like, compact Lie group. And let's say we're in this genus 0 case, but it could be higher genus or whatever. Then all of this stuff we did can be made G-equivariant. So all this finite dimensional approximation schemes, all of this stuff can be made G-equivariant. So in that sense, you can do G-equivariant Gromov-Witten theory. And you know, I don't know if anyone's done it yet, but I know that people have thought about it. Things like localization and stuff, you know, those sorts of calculations people do. I think this is possible using this technology, and you know, as I said, this, so you could construct an equivariant. You'll get, you know, an equivariant global Kuranishi chart for your moduli space of curves, and you know, that's perfectly fine, and there's no difficulty in doing that. You know, this line bundle L can be made equivariant. Finite dimensional approximation scheme can be made equivariant, and so all the equations and everything can be made equivariant. It's not a problem, and then you can use that to do computations and so on. That's perfectly fine. It's not a hard thing to do. When it comes to equivariant Gromov-Witten theory and orbifold Gromov-Witten theory, that I think there are some, I don't know if they're theorems or I don't know, but you know, there are questions in Gromov-Witten theory where you have a symplectic manifold and a Hamiltonian group action, and you look at this, you know, this moment map quotient, and you ask what's the relationship between, you know, what's upstairs and what's downstairs. But I'm not really an expert on that kind of stuff. Other people are, and there are papers, I'm sure, written about these kinds of things. I'm not the best person to ask about that, I don't think.
Thanks a lot.
Yeah.
So maybe we should thank Mark again for now and move to the informal part of the discussion, which